Welcome to the second Fun Math Workshop. Today I will talk about Fick's theorem, as well as show some examples of its use and some interesting applications. So let's get started. So first, let's take a brief look at the Fick's theorem's history. So Fick's theorem is named after Austrian mathematician Georg Fick, who discovered this result in 1899. And the result was popularized in 1969 by Hugo Steinhaus. And so before we introduce the statement of Fick's theorem, let's first define what lattice points are. So firstly, there are several frequently used types of lattice points. And so one frequently used type of lattice point is, or lattice system is the hexagonal lattice. And here is the square lattice, which is the most frequently used. And in the Cartesian coordinate system, we will define these lattice points as points that have integer coordinates. And so, for example, the point -2, 5 would be a lattice point because both of its coordinates are integers, but the point -2, 9/2 is not a lattice point because its y coordinate, 9/2, is not an integer. And so for today, we'll focus on square lattices. And so, does anyone have any questions? Okay, no, so let's move on. So next we have the lattice polygon. And a lattice polygon is a polygon in the plane whose vertices are lattice points. And such a polygon is called a lattice polygon. So what Fick's theorem essentially says is, so it lets us find the area of such a polygon given some quantities that typically were given. And so let's move on. So, okay, so this polygon right here is a lattice polygon because all of its vertices are lattice points. And let's go on to the next slide. But so before we go into the actual statement itself, let's first think about some ways we typically find areas of lattice polygons. For example, take this lattice polygon right here. How would you find the area of this polygon? Does anyone have any comments on how we can find the area of this blue polygon right here? All right, so Alan has a very good idea. And so he's saying that we can take a 4x5 in which sort of this polygon is inscribed in, and then subtract out the triangles. Does anyone have any other ways of finding the area? Okay, so I realized that some people here already know Fick's theorem. So let's first not use Fick's theorem because we haven't really gone over it yet. So what's a way we can find the area of this polygon without using Fick's theorem and sort of just kind of like using things that we know about areas and like So a hint is you can dissect this polygon into smaller polygons or specifically triangles. Okay, so I guess this is a little bit too obvious. So let's just go over the first way to find the area. So this is like the way we typically find areas of triangles in lattice points, because what we do is just like we divide the polygon into like smaller regions that we can find the area of. So here we have rectangles, triangles, right triangles specifically, which are easily or the areas are easy to calculate. And so in this case, we can find that the areas are 3 over here, 3 over here, 3 halves over here, 2 over here, and 1 and 2. And so this is one way we can find the area of this polygon. So basically just taking the polygon and dividing into rectangles and triangles, and we can find all of these areas relatively easily. And we can sum them up to find the total area, which we can get as 1 plus 2 plus 2 plus 3 plus 3 plus 3 halves. And so this gives us a sum of 25 over 2. And so this is one way we can find the area of this polygon. All right, so yeah, okay. Now let's move on to the method that Alan mentioned. We can kind of like inscribe this polygon into a rectangle in this way. So okay, so we basically complete this polygon into a rectangle. And in this case, you can find the total area of the rectangle and then subtract off the corner bits. And here we get these areas. We have 3 over here, 3 halves over here, 2 over here, and 1 over here. And these are just all using base times height over 2. And we can also calculate the area of this red rectangle, which is a 4 by 5 rectangle. And we can calculate the area to be 4 times 5, which is equal to 20. And once we subtract the corner bits, what we get is, again, 25 over 2. And as you can see, in both ways, we get the area to be 25 over 2. All right, any questions? All right, so now we've talked about 2 ways to get the area of a lattice polygon. That are kind of the ways that you would think about if you don't know Pick's theorem. But these ways of finding the area become much more difficult to apply if you're given a very wacky polygon. So let's take this polygon. Let me just draw a polygon in green. If you're given a polygon like this, I'm going to try to make it as wacky as possible. So if you're given a polygon like this, that looks like this, it's much harder to apply the techniques we just saw. Because if you were to divide it into triangles, you'd get a lot of triangles. And not necessarily all of these triangles would be easy to find the area of. And if you wanted to complete it into a rectangle, you'll get a bunch of extra bits. And these all make the area harder to calculate. So for this polygon, the area of the polygon is, as you can see, much harder to calculate using the techniques that we mentioned earlier. All right, so, well, in some cases, there's actually a way to find its area, and this leads us to finally state the Pick's theorem. All right, so we start by defining three parameters, which are b, the number of lattice points on the boundary of the polygon, I, the number of lattice points in the interior of the polygon, and a, which is the area of the polygon. Right, and remember that lattice points in this case are points that have integer coordinates. So we can't have a polygon that looks like this, just like kind of floating in space or something like this. It's like all of the vertices have to lie on a lattice point. In other words, none of the vertices can be floating in space. And so typically, given a polygon, we want to find the area. And in that case, we want to find A, which we claim we can find by finding B and I first. And this is kind of what Pick's theorem says. What Pick's theorem says about these values is that they're correlated in an equation. So we have A is equal to I plus half of B minus 1. And again, we have this polygon right here, which lies in a rectangular coordinate system or a square coordinate system. And this is the same polygon from before, actually. And from before, we calculated its area to be 25/2. And now, since it's a lattice polygon, we can actually find its area A by using Pick's theorem. And now, how would we do that? So first, we can notice that this lattice polygon has 5 lattice points on its boundary, which in this case are just its vertices. So we can write down B is equal to 5. And we can also find the number of lattice points there are in the interior of this polygon. We can count that there are 11 here. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have I is equal to 11. And now that we know what B and I are, we can calculate A to be equal to 5/2, or sorry, let's start with 11 plus 5/2 minus 1. And you can calculate that this is actually just 25/2 again. So we've confirmed that in this case, in this polygon, we get the correct area using Pick's theorem. So does anyone have any questions about the theorem? What is the proof for the theorem? All right, so we're gonna go over this. We're gonna go over a sketch of the proof in a little bit. And all right. Oh, and one thing to note is that boundary points don't have to be the vertices. There could be boundary lattice points on the edges of the polygon. And those points would count as boundary lattice points. They would count to the total of B. But they don't count to the number of interior points, because by interior, what we mean is that the lattice point must be strictly inside the polygon rather than on it. And of course, the interior points don't count to the number of boundary points either. And so what I mean is, if let's say there was a lattice point here, that would count to the total of B. And points on the boundary, like this one, don't count to I. I counts only these vertices, or these points, sorry. And so there are 11 of them. Okay. All right, so now let's go over a sketch of the proof. So first, let's prove the result for a rectangle with sides parallel to the coordinate axes. And we have this rectangle here, and suppose it has a length of m and a width of n. So here, m, and here, n. All right. And we know that its area is mn. So this is just kind of the area of a rectangle is the length of its width times the length of its length. All right. And so A is equal to mn. And the number of boundary lattices is 2n plus 2n. So we're counting these lattices on kind of like the edges and the corners of this rectangle. And there's a total of 2n plus 2n of them. And you can see this by noticing that here there are n lattice points. Here there are m lattice points. And then the same here for here, there are n lattice points here, and there are m here. And that's where 2m plus 2n comes from. So B is equal to 2m plus 2n. And we can also find I. I is the number of lattice points in its interior. And so what we're counting is this grid of it, of lattice points. And you can actually see that there are n minus 1 rows of lattice points in this grid, and each row has m minus 1 points in it. So what we can find is I is equal to m minus 1 times n minus 1. And so from here, we can see that these values actually satisfy Hicks' theorem. So in other words, mn is equal to n minus 1 times n minus 1 plus half of b, which is m plus n, and then minus 1. And you can expand this, and I'll add this all up, and you'll get mn. So this concludes the proof of Hicks' theorem for rectangles. And so how do we generalize this for any polygon? And so we're going to do this in several steps. So first, let's cut this rectangle in half through a diagonal. After we cut the rectangle in half, we get two right triangles. And since these two right triangles are identical in the coordinate plane in that quite clearly they have the same number of boundary points, interior points, and they also have the same area. So we can let their common number of boundary and interior points be B prime and I prime. So let me just write this down. Let's say this triangle has B prime boundary points, or not just any triangle, the triangle that we get when we cut this rectangle in half. So this triangle over here. Let's say it has B prime boundary points and I prime interior points and an area of A prime. Okay, so we know that, okay, let's actually say that A over here counts the number of, or the area of this total rectangle. The I over here counts the number of interior points for the rectangle, and the B over here counts the number of boundary points in the rectangle. And we want it to be this way because we already know that Pick's theorem works for rectangles. So let's just say that these three parameters are all for the rectangle. And from here, we also know that A prime is just half of A because we're splitting the rectangle in half and taking the area of that. So let me just write it over here. This is equal to half of A. And so we can half this equation because we already know it's true. And again, A, I, and capital A, capital I, and capital B without primes are just the quantities that we have for the rectangle itself. So this is actually just true. So we can divide the entire equation by 2. And what we get is this. And now let's write some equations, sort of. So let's pretend that this diagonal of the rectangle has k interior points on it, k interior points of the rectangle. So not including these points, not including the points on the corners. So let's say there are k over here. And on this diagram, there are 0, but you can actually, you can easily find a rectangle where the diagonal has more than 0 points on its diagonal. So let this be k, and we can write a few equations. So first of all, what does 2i prime count? 2i prime counts the number of interior points in this triangle plus the number of interior points in this triangle. So basically what we're counting is all the interior points except for the interior points that are on the main diagonal, because those count as boundary points for each of these triangles. So 2i prime is equal to I minus k. And we can get another equation. We can find that b prime, so this is one equation, and another equation is that b prime, which is the number of boundary points on this triangle, B prime is equal to K plus 1 plus half of B. And so why is this true? B prime is the number of boundary points on this triangle. So if we exclude the K interior points or the K interior points of the rectangle that are on the boundary of this triangle, what we'll get is this set of points that are on the boundary. And this is precisely one more than half of the number of boundary points on the rectangle. And you can see this by just symmetry arguments. And so now we have two equations. And let's use them to transform this equation. Oh, and we also have this third equation. So A prime is equal to half of I, and we can see that I is equal to 2I prime plus K. So this is half of 2I prime plus K. And then plus 1/4 of B, and B is just 2B prime minus 2K minus 2. Or we can write this as half of B, which is half of B prime minus K minus 1. And then minus 1/2. And when we write out this, when we expand this expression, what we actually end up with is I prime plus B prime over 2 minus 1. Let me erase this. So what we get is I prime plus B prime over 2 minus 1. And so now we've proven Pick's theorem for any right triangle. And this is very powerful. And we'll see it in a bit. So this is very powerful because a very similar argument basically tells us that if Pick's theorem is true for some polygons, we can glue these polygons together and Pick's theorem will still hold. And I won't go over the details of this. But any triangle like this, since Pick's theorem holds for Pick's theorem holds for the red rectangle and also for these smaller right triangles, we can use that claim to prove that Pick's theorem actually holds for any triangle. Because this triangle over here, we can kind of subtract the Pick's theorem equation for the rectangle by the Pick's theorem equations for these three triangles, these three right triangles. And if you do some careful analysis on what the values are, you can see that Pick's theorem actually also holds for this triangle. And there's just something that you need to check, is that if you have a triangle like this, you have to divide the rectangle in this way, because you can't divide the rectangle as shown in the diagram. So you'll have something like this instead. So these are just some details. And now we've proven that Pick's theorem holds for any triangle. And so now that we know that Pick's theorem holds for any triangle, we can triangulate. So let's first talk about what triangulating means. So when we triangulate a polygon, we basically divide the polygon into triangles. And we can do this for any polygon. And so we have this polygon over here. We can triangulate this polygon in this way. And because Pick's theorem holds for triangles, it holds for each of these triangles that are its parts. And since Pick's theorem holds for these triangles, it holds when we glue these triangles together. And so it holds for this polygon. And so that's basically the sketch of the proof of Pick's theorem. So if you have any questions, feel free to ask. All right, there haven't been any questions, so let's move on. So now examples. I'll show you guys some polygons here, and let's practice finding the area of these polygons using Pick's theorem. So here we have a polygon, which is a triangle. And as you can see, it looks like it has a very small area. So can any of you calculate what the area is using Pick's theorem? I'll give you guys a minute. Right, yeah. The answer is 1/2. So good job to all of the people who answered 1/2. That is correct. So let's just go over this real quick, since a lot of people already got the answer. We can find I, which is the number of lattices in the interior of this triangle. And as you can see, there are no lattice points in the interior of this triangle. So I is just 0 in this case. So this is equal to 0 plus B is the number of boundary points on this triangle. And as you can see, there are only 3, which are the vertices of the triangle. And -1. And once we calculate this, what we get is just 1/2. So 1/2 is the correct answer. All right, I'll give you guys another example. So here you have a polygon. This might be a little bit more annoying to count, so I'll give you guys 2 minutes on this one. All right, so does anyone need more time? If not, then we can go over this problem. The correct answer is 16.5 or 33/2. So good job to anyone who got that as their answer. And so let's use this theorem. So I is the number of lattices in the interior, and we can count this as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I is equal to 11. And next, let's count B, which is the number of boundary points. And again, on this example, there are no boundary points on the edges, except for the ones on the vertices. And there are, I believe, 13 vertices. Yes, 13 vertices. So B is equal to 13 in this case. And so just if there was a vertex, let's say over here, that would count into B. If there was a lattice point, and then in that case, B would be 14. But in this case, B is 13. So I just want to demonstrate that points on the boundary also count towards the total number of boundary points. Points on the edges, sorry. So again, let's calculate this. And this is 33/2. So good job to anyone who got the right answer. And just to showcase how much more difficult it is to use the techniques we mentioned at the beginning of today, how much more difficult they are in finding the area of this polygon, let's just divide this polygon into triangles and rectangles or trapezoids. So we can divide it in this way. And so down here, this triangle has a height of 1 and a base of 3. So this triangle has area of 3/2. This trapezoid has bases of length 3 and 6. And so the area of this trapezoid is 9/2 because its height is 1. And this trapezoid has bases of length 2 and 6. And it has height 1, and therefore its area is 8/2, which is 4. This triangle has height 2 and base 2, so its area is 2. And this triangle has base 1 and height 1, so its area is 1/2. And this one has area 1/2, and this one has area 1/2. And these two have area 3/2. And if you sum all of these up, you get, you still get 33/2. You get the same answer, but it's a lot more work because you have to split it into regions that you can easily find the area of. And it's not always true that you can find such regions. If you have like a very, very wacky polygon, it might be next to impossible to find a nice a nice partition of the polygon into smaller polygons that have areas that are easy to find. So this is why Pick's theorem is useful in some cases. Okay, now let's look at two applications. So our first application is in this problem. So can you draw an equilateral triangle whose vertices lie on lattice points? I'll give you guys 3 minutes to think about this, and afterwards I'll present the solution. Feel free to put any guess you have or any ideas you have in the chat. So do you all think that the answer is yes or no? Okay, so Ellen says, I don't think so, considering this triangle is not equilateral. Oh yeah, and this is true. You can find that these two, where this length is root 18, this length is root 17, and this length is root 17 also. So this is not equilateral. So this is just something to know. All right, so some people are saying yes, and some people are saying no. I'll give you all 1 more minute to think about this problem, and then I'll go over it. All right, now more people are saying no. So I guess it's time that I could start going over it. If you guys want more time, please say so in the chat. Can I have more time? Okay, sure. So I'll give you guys 2 more minutes. So try to think about how you could use Fick's theorem in this problem. All right, so 2 minutes are up. If anyone wants more time, you can ask. All right, so nobody's asking for more time, so I'll start talking about the solution. Yes, I will. Oh, okay. So if somebody wants more time. So I'll give you guys 1 more minute, and then by then, I hope you guys could be acceptable with me starting to present the solution. So I'll give you guys 1 more minute, and then I'll present the solution. All right, the minute is up. Someone said to apply Pick's law, use 3 lines and connect the same number of points on each one to make an equilateral triangle. I'm not completely sure what you mean by that. Oh, yeah, and I should probably present the answer to the question now. The answer is no. You cannot draw an equilateral triangle whose vertices lie on lattice points. So no matter how hard you try, there's always going to be a side that does not have the same length as the others. And so the way we can use Pick's theorem on this is because we have a polygon whose vertices are lattice points. And so we can apply Pick's theorem. And since this, let's just say, suppose this triangle over here is an example of an equilateral triangle whose vertices lie on lattice points. So we're using proof by contradiction. Let's suppose that this length is S. And you can easily see that the area of A, or the area of the equilateral triangle, which we will call A, is equal to √3/4 times S squared. This is equal to A. And at the same time, since this triangle right here is a lattice triangle, we can use Pick's theorem. So this is also equal to I plus half B minus 1. And now notice that S squared is an integer. So why is this true? S is the length of the segment that connects 2 vertices, or any 2 vertices of this equilateral triangle. And all of these vertices are lattice points. So if you use distance formula on this segment, you can see that the segment is the square root of some integer. And so S squared is an integer. In this case, we can also just see that by Pythagorean theorem, S squared is equal to this side length squared plus this side length squared. And both of these side length squares are integers. And so S squared is also an integer. And at the same time, I and B are both integers as well, because I counts the number of interior points which cannot be say a fraction or any other thing like that, I has to be an integer. And B also has to be an integer because B counts the number of boundary points. And you cannot have, say, like 3 halves boundary points. So I and B are also integers. And so this thing right, this expression on the right, this expression is an integer plus half of an integer minus 1. And so this expression right here has to be rational. And in fact, this expression has to be half of an integer. But let's just say that this is rational. Let's write this. This expression is rational. And so A is rational. But we can see that since s squared over 4 is rational, and this is because s squared is an integer and 4 is an integer, so s squared over 4 is rational. But the square root of 3 is not rational. It's irrational. So this whole thing right here is irrational. So at the same time, A is rational, and A is also irrational. And this is nonsense. We cannot have a number that's both rational and irrational. So such a triangle does not exist because what we started our proof with is an assumption that such a triangle exists, such an equilateral triangle exists. But we have a contradiction. And so what we assumed was wrong. And therefore, there are no equilateral triangles whose vertices lie on lattice points. All right, any questions? All right, no questions. That's it for today. This concludes our second LogiStem Fun Math workshop. If you want to attend more of these workshops, again, you can check on our website, logistem.club. And the next Fun Math workshop hosted by Jennifer will be on August 5th, August 15th, which is next Sunday at the same time. And I hope you all had fun and learned something new today. And as always, thank you for attending and hope to see you all soon. So thank you all and have a great day.